go over the quiz. If the value, I have all the quizzes done. The value of quizzes grows according to this function. V equals K times E to the 0.5 times the square root of T. So the future value of trees could be described by this function. The continuously compounded interest rate is 0.05. When should these trees be cut down? By the way, there is an implicit assumption I'm making here. I'm assuming that the trees can't be replanted. In a more extended model where you could replant the trees after you harvest them, it would change the problem slightly. So we're implicitly assuming that. Then, in this case, we want to maximize the present value of the trees. The present value of the trees is given by A. That's just the future value times e to the minus RT. Then just substituting in, notice what we get for A. A is equal to K times E to the 0.5. The square root of T is T to the 0.5 power. The times E, R is 0.05 minus 0.05. This simplifies a little bit to A equals K times E to the 0.5 to the 0.5 minus 0.052. Since this is the same base, you just add the exponents. Just like x to the a power times x to the b power is x to the a plus b power. So you're just adding the exponents. Okay. Actually, the way we did this problem, I think it was yesterday, maybe it was the day before, I can't remember. The way we did this problem earlier was we just took a dA dt, set it equals 0, solve for the critical value, and then verify that the second derivative of the a with respect to t is negative. Let me show you a slightly easier way of doing it. Let's take the logarithm of a. The logarithm of a is just going to be the log of k plus the logarithm of e raised to this power. Now notice
that first t should be raised to 0.5, right?
No, okay, I'm sorry, absolutely right. This is, I left that off, thank you. There we go. Okay. And notice, maximizing log A will also maximize A. Because the log of A, as A gets bigger, log A gets bigger. So you could maximize the value of log A, and that would give you the maximum value of A. The value of t that maximizes log A will also give you the maximum value of A. Because log A is a monotonic transformation. If you look at the graph here, here's A, here's the natural log of A. This function would look like this. It's always rising. So the highest value of A, the highest value of log A, rather, will give you the highest value of A. Okay. That trick makes this a lot easier to do. So let's maximize log A. Then take the derivative of log A with respect to t. Actually, let me do one more thing. How could we simplify this equation right here?
Bring down these exponents.
Yeah, let's do that first. Notice log A is equal to 0.5 t to the 0.5 power minus 0.05 t. Times the log of e, which is 1. So there is log A. Now you want to maximize log A, and do log A dt. Would just be 0.25 t to the minus 0.5 minus 0.05. Set this equal to 0 and solve for t. And doing that, we get multiply both sides by t to the 0.5 power. And then we get 0.25 t to the 0, which is 1, equals 0.05 t to the 0.5. Divide both sides by 0.05, and you get 0.25 or 0.05 equals the square root of t. This is just 5. Square both sides, you get your critical value t is 25. Of course, we need to look at the second order condition too to make sure we have a maximum. If you take the second derivative of this, d log a squared dt squared, the second derivative, notice it's just minus 0.125 t to the minus 1.5. This is always negative. So this guarantees that at t equals 25, you maximize the present value of the trees. And this is a slightly easier way of doing it than the way we did before. But you get the same answer either way. This is easier though. Now, let's go back. The other part was about the growth rate of V. You have this equation, V equals K times E to the T to the 0.5 power. Take the log on both sides. Log V equals log K plus the log of E raised to the square root of T power. And now take d log V dt. d log V dt let's simplify this again before I do this. Notice we could write log V equals log K plus T to the 0.5 power times the log E, which is 1. So d log V dt is just 0.5. Oh, wait a second. Wait, I made a mistake here. Somebody pointed it out. This is not our V function, is it? Our V function is really 0.5 times this.
Yeah.
I'm doing the problem we did in class, not the quiz problem. So let's go back. The proper V function is this. It'll be the log of E raised to the 0.5 times the square root of T. Or it'll be log K plus 0.5 Therefore, d log b dt is 0.25. T to the minus 0.5. Okay. That's R sub B, the growth rate. Okay. When do you want to cut down the trees? When the growth rate of the trees is just equal to the market interest rate. Here, the market interest rate is 0.05. So set this equal to 0.05. And solve for t. It's the same equation we just solved for. So you would get t equals 25. The only thing you have to be careful of if you use this approach, notice there's no second order condition. So what you have to be sure of is that the growth rate of the trees is declining over time. And it is. Because this is really just your first order condition. If you graph the growth rate of R sub B, it looks like this. And if t equals 0.05, this crosses right at 25. So you cut down the trees again 25 years. Okay. Any questions? Okay. Problem number 2. Josh has this utility function that's given by u equals 210 times x minus x squared plus xy plus 121 minus y squared. Where u is utility, x is the amount of, let's say, good x consumed, y represents the amount of good y consumed. Okay. Find and explain the meaning of the following derivatives. U sub x. Well, u sub x, by definition, is just partial u partial x. Or in economic terminology, u sub x would be what?
Changing u for changing x.
The marginal utility of good x, which would be the verbal interpretation, the additional utility you would get, roughly speaking, from consuming one more unit of good x. The derivative of utility with respect to x, the rate of change of utility with respect to x, really is simple. Okay. And mathematically, it's easy to get this. It's just 210 minus 2x plus y. And let's assume that Josh wants to maximize utility. Then what should we do with this partial derivative?
Set it equal to 0.
Set it equals 0. Okay, but actually we're jumping ahead of ourselves. We're doing the next part. So just hold on to that for the moment. I also asked you to interpret u sub xx and u sub xy. What is u sub xx? Okay, let's just first give the explanation of what it is. What does u sub xx mean? By definition.
Changing the marginal utility of X for a change in X.
Yes. Or another way of writing it is, it's just the partial derivative of use of X with respect to X. And since use of X, as Zach said, is the marginal utility of good X, this measures the rate of change of the marginal utility of good X as X changes. Okay. Roughly speaking, you can say, what happens to the marginal utility of good X as you consume one more unit of good X? Use of X. It's a second derivative. And what is the value of this second derivative? Brianna? Negative 2. Just take the derivative of this term right here. With respect to X, it's negative 2. So what does that mean in simple words? If the use of X axis negative. In economic terminology, we would refer to this as what? Diminishing marginal utility of consuming good X. The more X you consume, the lower the marginal utility of good X, diminishing marginal utility. It's like these donuts. Some of you have had one or two. Imagine eating a third, fourth, a fifth. By the time you get to that sixth donut hole, most of us at least, would really be suffering a diminishing marginal utility. That would limit it. At some point, we might actually get satiated. And that would mean we would reach the point where the marginal utility of these donut holes is 0. You wouldn't want to go past that. Because then the marginal utility maybe would become negative. And so your utility would actually be going down, as you can see. That's use of XX. Use of XY, I think that's the one I asked you. Did you?
Use of YY.
Well, I didn't actually. Let's ask that. On the quiz I didn't ask that, but I could have. But use of YY would be what? We could do that. First, we would need to get use of Y, wouldn't we? Use of Y is that, you want to change the quiz. Use of Y is what?
X plus 120 minus 200.
Okay, it would be X, differentiating this term here with respect to Y, plus what's the rest of it?
120 minus 2y.
Minus 2y. And had I asked for use of YY, what would that be? Negative 2. Actually, we need a use of Y anyway, because I asked what is use of XY. This is a cross partial derivative. By definition, this is partial u sub y divided by partial x, or differentiated with respect to x. That's a cross partial derivative. We've got use of y here. So use of xy is what? Mathematically, use of xy will be 1. So it's positive. So what does that mean in words?
The marginal utility of good X, or good Y, will increase as consumption of X increases.
Right. The marginal utility of good Y will increase with increased consumption of X. And by the way, by Young's theorem, we know that uxy equals uyx. And actually, you could verify that here. Here is use of x, or did we erase it? No, here it is. Here's use of x. So what is use of yx?
Still just 1.
1. Take the derivative of this, use of x with respect to y. It's 1. So this means as you consume more of good x, the marginal, excuse me, is
Marginal utility of good X.
marginal utility. Wait a second. Let's write it in. You said it right.
Sorry, you get it.
As you consume more of good Y, what happens to the marginal utility good X? It goes up. So it's both ways. Okay, both ways. Okay. Now, let's get back to the optimization problem. We know Josh wants to maximize his utility. He should consume amount of X and Y, or use of X is 0, or the marginal utility of X is 0. What else should Josh do? Let's do. This is one first order condition. What's the other?
Is that you want, use of Y equals 0?
Yeah, use of Y. And use of Y is just partial U, partial Y. And partial U, partial Y is just what? Let's put the 120 term first. 120 plus what?
X
X
minus 2.
minus 2y. So you have two linear equations and two unknowns. Yesterday I taught you Cramer's rule. So let's use Cramer's rule again to solve for X and Y. Whenever these equations are linear, you could use Cramer's rule to solve. Let me just rewrite this equation here in a slightly different format. Let me bring this and this over to the right. And then we have 2x minus y equals 210. Doing something similar to this equation right here, bringing these two terms over to the right, we get minus x plus 2y equals 120.